Today we will be talking about this capillarity and surface tension, and this is an interesting topic because when I was kid, I used to play with, those days we had this thermometers which are of mercury. So it's to break the thermometer, and the mercury is to spill, and then I used to play with the small drops. Always I was curious why they are forming so naturally one of the least spherical shape that you can imagine, and that's because of the surface tension. And nowadays, of course, you can't handle mercury; it's hazardous. But those days it was pretty good. Okay, as a kid, I used to play with these things. So, in this topic, what I will do is I will provide you some of the understanding of why surface tension really matters in terms of our understanding of fluid flow. So if you look at this field, was started by in early 19th century by two famous scientists. One is Pierre Simon de Laplace and Thomas Young. So Laplace and Young pretty much establish this field of surface tension and capillarity. Okay. So if you think of a liquid gas or a vapor interface, so this is the liquid gas interface, and if I look at the molecule, which is a water molecule inside, what I see is this water molecule is attracted by the neighboring water molecule, water molecule inside the liquid. So inside within the liquid, they are attracted. So another neighboring molecule, they are attracted. So what I see this is in some sort of a happy state, because it feels good. It is always attracted by another water molecule due to its neighboring cohesive forces. Whereas if I look at the water molecule which is sitting at the interface, the same water molecule which is sitting now at the interface, which is partly in the liquid, partly of it is in the gaseous phase or in the vapor phase, you see that similarly you have the attractive forces or the attraction only on the half part of the water molecule, okay? Because the other half part, there is no water in it, right? So it is in the gas or air or in a vapor phase. So only half of it is getting attractive forces by the neighboring water molecule. So this molecule essentially is in unhappy state, because it's not able to find another pair in which they can create an attraction, whereas this one is always, you can see the other liquid molecules inside. So this is really the fundamental crux, as I was mentioning when I was kid, was playing with this mercury, and the drops I see, they were forming very small tiny droplets. This is crux to it. No one wants to be unhappy, right? Everyone wants to feel good, happy. So that's the innate nature of the liquid interface is that it will try to distort that interface in such a way that minimum area is exposed. Because if moment I have exposed area in a liquid means molecules are in an unhappy state, and I don't want to have that. I always want to be in the water molecule wants to be always in a happy state. So it will try to make sure that the interface changes in such a way that this amount of unhappy molecules are the least. Okay? So that's why we see that they form curvatures and so forth, so that they form these small droplets. Okay? So the least surface area we see. So we can say that the liquid they adjust their shape in order to expose smallest possible area. So this is quite fundamental to our understanding of the liquid system. Now, if you think of in terms of the energy, if I associate energy for these molecules which are inside the liquid, if I associate an energy U, which is the energy of the cohesion energy of the molecule. So if U is the cohesion energy of the molecules that are inside, okay. So at the surface, what is the amount of energy that the molecule is essentially, what will be a difference, or in terms of what is the energy that is less compared to what is inside the system. So it will be sort of U by 2, right? So this cohesion energy, it will be less by U by 2 because of half of the interface, or the half of the molecules are exposed to another phase. Okay. So we can say that the surface tension is essentially a direct measure of the energy shortfall per unit area. So we can say that the surface tension is directly related to the energy shortfall in this case it is U by 2, the energy shortfall per unit surface area. Okay. So now, if I have the molecules that we are considering, say if A is the typical molecular size, okay, or the characteristics, typically these will be known to you. So this is the molecular size. So if A is the molecular size, then the area that is exposed is somewhere around A square. So my surface tension, so I can write gamma, the surface tension is equivalent to U square, the energy shortfall. U square by 2 is the energy shortfall per unit surface area, where A square is the area exposed. If A is the molecular size of this, be water or any ethanol, whatever the liquid may be. So if A is the molecular size, then I can say that gamma or the surface tension. So, this is how surface tension can be related to u square by 2a. Okay. Is that clear? So, essentially it goes back to our understanding of the previous lecture, where I talked about interaction forces between molecules and atoms. Okay. So, if I think if this is an oil, for example, a silicon oil or a heavy oil of this nature, what is the predominant nature of interaction between these oil molecules inside the system? Is a van der Waals interaction, right? So, if you look at, say for example, oil, so for oil, if this liquid was oil, so mostly the interaction is van der Waals. So, U can be scaled as how we can scale U. If this is the van der Waals kind of interaction, last time we talked about it. Yeah, that's a range, but how it will scale, we talked about it, right? So, there was a hydrogen bonding question and things like that. It scales with kT, correct? So, U, the cohesion energy, can be scaled as kT, the thermal energy. So, if you look at the value of kT at 25 degrees C, typically the value of kT is somewhere around 1/40 electron volt. Okay. So, if I plug this gamma, if I know the molecule of the dimension of the oil molecule, so I can plug this in because my kT is around 1/40. So, I can say that the surface tension for oil at room temperature will be close to 20 millijoules per meter square. Okay. So, energy per unit surface area. So, that is how I am defining the unit of surface tension. Okay. So, is energy per unit area. So, based on various fluid, I can really can look at this surface tensions. Okay. For water, for example, we talked about in water what we have is the hydrogen bond. Okay. So, what was the amount of hydrogen bond? The cohesion energy we looked at is almost like 10 times of the kT, correct? So, I expect that the hydrogen bond, the cohesion energy is large. So, I can expect my gamma for water would be somewhere around say 72 millijoule per meter square. Okay, because the energy now is larger because of the hydrogen bonding, it is 10 times kT. So, it can be like this. Yeah.
So, hydrogen bonding is not similar for all kinds of molecules.
Right.
For example, in hydrogen bond, the hydrogen bonding is something different than hydrogen-oxygen bond. So, how can we generalize the energy for a hydrogen bond in these cases?
So, in this case we know for water molecules, in this case we are talking about the water molecule surface tension, right. So, the water molecules through the cohesion is through the hydrogen bonding, right. And we yesterday's lecture we looked at it, we said that that amount of energy is close to 10 times kT, correct. So, then my U is now scales as 10 kT. Okay. So, I plug this in 10 kT divided by 2 times A, the molecular diameter of water we already know, right. So, if you put those value in, then I will see that it comes to 72 millijoule per meter square. For any other where there are different hydrogen bonding, then my U will change, and the correspondingly for that the molecular size of that molecule itself will also change. Is that clear? For mercury, which where I started my talk today, where I was playing with mercury. What kind of mercury is what kind of is a liquid metal, right? So this in liquid metal, what you expect in terms of cohesion energy? They should be large, right? So in liquid metal, U or is close to the interaction cohesion energy is almost close to 1 electron volt. Okay, it's very large. So if you look at typically oil is 1 by 40, but this is almost 1 electron volt. The cohesion energy is this is very large. Okay, so that's why we see that for gamma for mercury is almost close to 500 millijoule per meter square. So based on that fundamental interaction energy, I can see from oil to water to liquid metal, I can have some understanding or some rough estimate of what a surface tension value should be. Okay. There are various other definitions as well of surface tension. As this has been mentioned, this is the free energy per unit area of the interface that needs to be formed. So you need to provide some energy to increase the surface area by unit, so by unit area. So that also can be represented as the in terms of the surface tension. So one can, in terms of this free energy, one can look at the surface tension in terms of the increase in internal or the free energy. So gamma can be defined as del F del A, where F is the free energy at a constant temperature, total volume, and number of molecules. So N is the number of molecules, V is the total volume, T of course is temperature, and F is the internal or the free energy at the interface. Okay. So whenever I have an increase in area, so it is saying that whenever there is an increase in area, that can be associated with the surface tension. Okay. So in chemical, since you guys are in chemical engineering, some of you, so you may have heard this something called a grand potential, which is omega is defined as F minus N times mu. What is this mu? Chemical potential. Okay. So this can be written as this mu is the chemical potential, and that can be related to the state as minus P times the volume plus gamma times the A. Okay. So there are various forms of this potential one can write as well in terms of the grand potential. Okay. So, the next thing that is this clear? Any question on this? So, there are various ways to look at it, and also I should mention that it is also a surface tension can also be defined as the force per unit contact length, okay? Contact line length. So, then you have a unit of Newton per meter, right? As so, gamma can also be defined in terms of a mechanical way. So, that is a mechanical description of a gamma can be defined as the force per unit contact line length. I can also define that as a Newton per meter. So, you have seen instead of millijoule per meter square, often you will see in the textbooks and so on is defined as Newton per meter, but the energy is more fundamental. Okay. So, when you see this picture, I believe you have seen this picture, in textbook and so forth, like this kind of picture as well. So, when you see this picture, one thing it should appear to you is that, well, this molecules, they are all cohesion energy and so forth. So, that is fine, but if I look at the interface, I see that along the interface, which is tangential to the interface, along parallel to the interface, this is balance. But if I make a force balance across the interface, top and bottom, I see that there is an unbalanced force, right. So, if I understand free body and so forth, then what will be the direction of the surface tension force? Upward, right? But is the surface tension upward force? Then what is happening? So, question is, so there must be something going on here. So, the question is, why is surface tension a force parallel to the interface? It's a fundamental question. We often take things for granted, right? But you have to think deeper. And if this is a representation, then what is going on in here? Is there something fundamentally we are missing? This is cohesion, right? So, this is the adhesion force. Carved?
It's a kind of reaction force which is used to balance the.
Where is that reaction force? I don't see any reaction force. Huh? No, that's kT. That's a cohesion, right? So, the energy, the cohesion energy scales as the thermal energy, right? kT. But this is the force picture, correct? So, I see an unbalanced force. There is something going on in there. So, you have to think closely in your understanding of your, say, fluid mechanics in second year and things like that. So, if you recall, in fluid mechanics, when there was a fluid element inside the system, you have drawn some control volume, right? So, did you draw something like cohesive force? No, right? So, what you have drawn in that control volume essentially? Pressure force. So, what is that pressure force? It is a repulsive force because it was acting in the opposite direction. So, what you have in the bulk, within the bulk, you have a repulsive component, right? Which in the bulk, so there is a repulsive component. So, in bulk or everywhere, the repulsive component balance with adhesion component. Okay? And the origin of this repulsive component is purely from the from the pressure that we understand. But in the if you look at in the other case, if this has to have a perfect balance, then it doesn't say that this repulsive component close to the interface needs to be balanced out. So, at the interface, the repulsive component along this may fairly balance out, but within the molecule they don't need to be of the same magnitude. So, that difference actually helps to balance out any unbalanced force in the vertical direction, but at the net effect is, since everything is balanced, so now there is a repulsive component which is of a shorter magnitude compared to the cohesive component. So, you have a net force which is parallel to the interface acting to the adjacent fluid molecule. Okay? So, that creates, so this unbalance along the interface between attractive and cohesive force creates the net force being parallel to the interface. Okay? So, this, unless we don't have the picture of the repulsive component of the forces, we will have a misunderstanding that always, based on the force picture that which the picture everywhere in the textbook is drawn, there is an unbalanced force, but it's not true. Actually, the net unbalanced force, because the attractive forces are much stronger compared to the repulsive forces, because they are close to the interface, versus where in the bulk, right. So, in the bulk, the repulsive forces balance out with the attractive forces, and that's where we see there is a net force parallel to the interface. Okay. So, just alone this kind of picture without those red dotted or dashed line doesn't provide the complete story. So, now you can confidently say that, well, the molecular description, what I call it as a molecular description of the of a surface tension, really makes sense, because this is the molecular description, because as a macroscopic quantity, which is essentially a mechanical definition, force per unit length is always along the interface. Okay? Clear? Let us look at some few things. How one should measure this surface tension, right? The next question one can ask. how to measure this surface tension. So, a quick and easy way to measure a surface tension is to really calculate a force. If I have a, say, a plate, so this is the liquid, this is the gas or the vapor, we can make it a V, the vapor, liquid, vapor. Vapor is essentially air and things like that. So, if I have a plate and if I want to withdraw the plate, the force that is required to withdraw the plate should give us the measure of the surface tension. Okay? So, think of it, you have a bucket of water, you have dipped a plate and you want to pull that plate. So, that will give us the measure. How? Okay? So, if you look at so at the interface of this is the solid, this is the plate. There will be surface tension forces which will be inward, which will be the gamma LV. So, gamma LV refers to the surface tension of the liquid vapor interface, which we known as, say, surface tension of water. When I say, essentially what I am saying is the surface tension of water in air. Okay? So, in other words, gamma LV. So, if I look at the work, so if I look at the total amount of free energy, so change in free energy due to the lifting of the plate by change in lifting the plate amount dl. Okay? So, I lifted the plate with an amount dl. So, there will be a change in the free energy of the system. Okay? So, that change in free energy dF, what will be that change in the free energy? So, free energy, remember, so it is coming from that U, right. So, U, our cohesion of the free energy is cohesion energy is can be measured in terms of the surface tension times the area, correct, the exposed area. So, if I withdraw this plate, what happens to the my change in free energy? So, some energy gets created, some energy get lost, right. In other words, what is the new area that I have created? So, if I withdraw, so there will be some area which will not be non-weighted, right, because there will become, it will be exposed, the plate will be exposed to the air, correct. So, that is the new area, and the area that I have, or the energy that I have reduced is the one which was previously covered with the water molecules, correct. So, if that is the case, I can write this as gamma solid vapor. This is the new that I have created. I have lost gamma solid liquid that I have lost times, if the W is the width, the dl. Okay, is that correct? The width is the W is into the board. Okay. So, this is my change in the solid vapor. S referred to the solid. So, this is the plate, this is the solid vapor. I have created a solid vapor and I have lost the, because now no longer that solid liquid is in contact. So that's the dry part, so I've lost that. Okay. So the force, if this is the change in the free energy, if I have to, I know that if I have to the work done, if I have to move with a certain distance dl, will be w times dl, right? So then this represent, so this entire quantity will be the force. Okay. So this must be the force that is needed to move the plate. Now let's look at carefully about what is happening at the contact line. So at the contact line, so if I look at, I am now focusing in here. So this is my contact line. So I am focusing right at the contact line. So at the contact line, I have the solid surface. This is the solid. This is my liquid. So essentially, if you think of, if you focus, this is almost, there is a wedge, okay, and that wedge is at an angle, say theta, correct? So I have a wedge of liquid at an angle theta. So along the liquid vapor, and this is the vapor, I have the gamma LV. Along this vapor solid, I have the gamma SV, and along here I have the gamma solid liquid. Correct? So this is the solid vapor surface tension, solid surface tension. This is my liquid surface tension, and this is the solid liquid surface tension. Okay. If I look at, this is the contact line. So this is what represents at the contact line. So it creates a wedge. I can see that there is a wedge, and can represent this in this form. So you have the solid, liquid, and the vapor. If I do a balance of this, what I get is a gamma LV cosine theta. So gamma LV cosine theta has to match with, so LV cosine theta has to match with gamma SV minus gamma SL. So if I look at this, the amount of force, you see that the amount of force has this quantity gamma SL, gamma SV minus gamma SL, right? So I can see that if I replace this in here, then the amount of force needed to move the plate will be nothing but gamma LV cosine theta times W. Correct? Gamma liquid vapor, I know, right? If I has a water, I know what is the surface tension of water. I can measure this. I can find out what is my theta. I can measure this. W is known. So then entire thing is known. I can basically, if I can have a way to measure the force, I can, unknown quantity, any liquid, I can measure the surface tension as well. So this is the principle used for tensiometer. So tensiometer works on this principle to measure surface tension for any unknown liquid. Any question on this? Is it clear? Yeah.
So shouldn't it be 2W or at least P? Like we are writing the depth of the plate as W, but the plate is of three-dimensional.
2W. What is 2W is coming in?
So the plate is exposed at all the surfaces to the solid vapor.
But this is symmetry, right? So here, whatever is happening in here, this is also symmetry, right? So this problem is essentially what I have done is I have a plane of symmetry. So here, this is a good question actually. So what I have done is essentially cut this plate because this is my plane of symmetry, and I have looked at this part of this, correct? So if you have to account for 2, then essentially the force will everything will be 2W, 2 here, right? So then again the 2 will cancel and you will end up having the same thing. Is that? What is that? Yeah, this part what we are looking at is that's a very good point. So essentially we are worried only about the length that is exposed over the width of the system, right? So this is really a thin plate that we are talking about. Very good point.
Sir,
yeah.
Shouldn't there be twice in the DF?
No, that's what I'm saying. There is not twice because there is a plane of symmetry. If you take twice, it can be very well be twice.
We are just considering for one set.
One plane of symmetry because it's a plane of symmetry. So if you take twice of this, everything will be 2, 2, 2. So 2 will eventually cancel, and you will still have the force required will be still gamma LV cosine theta.
No, so we are talking about the free energy quantity. It should be twice of that.
No,
So because
this is the change in free energy, right? So this quantity is not the total free energy; is the change in free energy. So that's the dF quantity. So in that dF quantity, there cannot be 2 there. Is it clear? Because that's the change. So change in the free energy. Because you remember the gamma, how we have defined gamma. Gamma is the change in the free energy over the change in area. Okay. So that's the change we are talking about.
so what is W? W is the width of the perimeter.
W is the unit with depth into the plane, right? So that's what our area is. So W is essentially talking about the area of the system, right? W times dl, right? That gives us the area. Is that clear? So we are talking about the change. It's not just the free energy, the change in the free energy. Okay. Let me just okay. We can talk about this later a little bit later. Now think about. Can I erase this? Is it clear? Think about oil, say oil in water emulsions. Okay. So what we want to understand is something called the Laplace pressure. So what we have is say a droplet. So typically there could be emulsions or two-phase fluids. So either can be oil in water or water in oil emulsion. A good example of emulsion that one use, paints, mayonnaise, right? Mayonnaise that you use is an emulsion as well, is a water in oil emulsion. So typical, let's look at a drop of oil in water. Okay. So what you have is this is the oil drop which is in the surrounding water media, okay? And there could be numerous of such oil drops to create an emulsion. And of course, the oil drop will always be spherical, because that is the least lowest energy state, right. So, it is to reduce its surface energy, so that it is in the spherical shape. And let us consider that it attains the the lowest energy state, or this will in terms of surface energy with a radius r. If I displace, or in other words, I allow this oil droplet to grow by an amount dr. Okay. So, I allow the oil to grow in the water media by an amount dr. So, what will be the work done? Work done del W. So, what will be the work done in this case? No, that is the only one. What else is there? So, there will be pressure volume, right. So, there will be P naught dV naught, okay. Then the pressure of the water times the volume of the water, and then the gamma oil water, right, and I have created an additional area, right. So, I have increased the area, which is the dA, correct. So, what is this dV naught? What is this quantity? So, how much I have increased the volume? 4 pi r square dr, right. So, 4 pi r square dr, and that is related to the, if I increase the oil volume, means I have shrunk the water volume. So, that is related to minus d of V w, right. Okay. What is happening to the dA? How much I have increased the area of 8 pi r dr, it's good, 8 pi r dr. So, the oil drop in any emulsion is in equilibrium, right. So, if it is in equilibrium, what we can say about dW? That has to be 0, right. So, in mechanical, for mechanical equilibrium, has to be 0. Then what is happening to delta P, which is essentially the pressure of the oil droplet minus the, or the pressure difference between the oil and the water.
So shouldn't the work done there be plus P naught dV naught, because the oil is doing positive?
Yeah. So, essentially it becomes minus, that becomes positive, right. This is minus d V w, right. So, then this minus becomes positive, right, and that is how you have 4 pi r square dr as a common, and then you have P naught minus P naught plus P w is the same thing. So, what is happening to this? Delta P is nothing, there has to be some quantity. Pressure, there must be some pressure difference across the oil water interface. 2 gamma, so everything cancels out, 2 gamma oil over R. So this is what is referred to as the Laplace pressure of the oil drop. Okay. So we have just derived from fundamental the Laplace pressure. Okay. So you can see that for aerosol, your radius is close to 1 micron, very small drop you can create. So delta P, the Laplace pressure, will be close to 1 atmosphere. So in an emulsion, this is the amazing part. In emulsion, the smaller drop, okay, if the R is small, the Laplace pressure is so large that they disappears compared to the larger drop. Okay. So this is often referred to as Pickering effect in an emulsion. So this, so the small drops are thermodynamically unstable because of the because of such a huge Laplace pressure. This is what you see in making of these emulsions. So often this referred to as Oswald ripening. So this is in chemical engineering, this process often been used in making these emulsions, and they are referred to as Oswald ripening process. Okay. And it's purely driven due to the these kind of Laplace pressure. Is that clear? Question? So the next thing is very important is the concept of this wetting, in the sense that if I have a liquid, how it will wet the surface will be dictated by something which is referred to as the spreading parameter. Okay. So the S in here is the spreading parameter, which is essentially talking about again the energy between the dry energy of the substrate minus the wetted energy. So if the substrate, for example, this is a substrate, right? It has an energy which is the dry energy. I bring a drop into it, now it becomes wet, it attains a different energy. That difference of the energy is referred to as the spreading parameter, and that spreading parameter will really dictate. For example, this is a common thing you have seen. If you drop water on glass, right, what do you see? Water completely wets, right, completely spread. Whereas the same drop of water, if you put on a plastic, it from drops, which is partially wetting the surface, right? It doesn't completely spread the surface. It is purely governed by this spreading parameter. So what is this spreading parameter? So if I have a dry substrate, so initially my energy will be the gamma SV, the solid vapor, that's the total energy. Now what I have happened? Now the new state is the wet state. So the solid is now covered with the liquid. So this is the solid liquid, that's a new energy I have created, and on top of that there is another interface I have created, is the liquid vapor interface. So I have added the liquid vapor interface. So that is the critical part. So these two difference will really dictate whether you will have complete wetting. For in case of glass, this value is greater than 0. Okay? So that's why you have complete wetting. Whereas in the plastic, there is a partial wetting. You still have drops, wetting a part of the plastic, because that is less than 0. So if you are given any pair of liquid and solid, based on the surface tension value alone, you will able to know whether that liquid will wet completely or it will have a partial wetting. So that's why the spreading parameter becomes a very important thing. In this context of the spreading parameter, when a surface is wetted by a fluid, those surface, what we call it is high energy surfaces. Okay. So high energy surface means those which gets wetted. Okay. For these high energy surface, the chemical binding energy is in the order of 1 electron volt. Okay. So they are really high, on which all liquid, so this is why high energy, so all liquids spread. So if you look at it like a glass is a high energy surface, because most of the liquid will wet the glass. Okay. It's a high energy surface. So they are typically made of materials that are ionic, okay, covalent, you will have covalent bonding, or metallic. Typically, the solid surface tension for these kind of we know that is energy of the binding, scales as energy of the binding over the diameter, molecular diameter square. They range typically from 500 to 50,000 or 5,000 millinewton per meter. Okay. So these surfaces wets everything. So the other thing that today's world we are very interested is something called super oleophobic, super hydrophobic, super omniphobic. So in other words, they repel both water and oil, so they will not get wet. So those surfaces we call it as a low energy surface. So is a counterpart of this is a low energy surface. Okay. So for this, the chemical binding energy is in the order of kT. Okay. So these are hardly wettable. Okay. Like plastics and so forth. So if you look at their solid surface tension, gamma SA of this will be scale as kT over a square. So that will be somewhere around 10 to 50 millinewton per meter. So there is a vast difference between a high energy surface which wets everything compared to a low energy surface which doesn't wet anything, okay, and is again related to the binding energy. We can equate that. Now, from the material characteristics point of view, yeah.
So, what is this binding energy between the solid and liquid, or between two solid molecules?
This is the binding energy of the. So, remember we have. So, in the liquid we are talking about cohesion energy. So, similarly solid will also have, it is made up of molecules and atoms. So, they will have the energy. Remember we talked about various forms of forces that are present and the energies that are present. So, this is the binding energy of the molecules that are consisting of that solid. Okay. So, this is the solid surface tension. Okay. Solid, A is the air or the vapor. So, gamma SV or gamma SA is essentially the solid surface tension. Okay. So, when we talk about say surface tension of water, we means always water with respect to vapor. So, similarly, if I talk about solid surface tension, means the solid with respect to the vapor. Okay. Only thing will be different is the solid liquid. So, then we have to specify is the solid liquid surface tension. Is it clear? So, if we look at the we talked about this concept of polarizability of the molecules, right. So, that is the fundamental in the molecular structure, that is what it dictates. And if I know the polarizability of the molecules, so I can really create surfaces which will either be a high energy or low energy or intermediate of this. So, I can play with surfaces that can have various level of polarizability to allow me to wet or de-wet and so forth. So, as for example, a quick fix, if I have to make a surface which is high energy to a low energy, often what people does, they put some fluorinated compounds into the surface. Okay. So, essentially what I am doing, I am changing the polarizability of those surfaces. So, let us see how the polarizability of the surface will change the spreading parameter. Okay. Is it clear? Can I erase this? So, we have learned this earlier in the last lecture. So, you can see how things are, the molecular understanding of matter can be interlinked with so many different aspects of the physical processes. So, let us consider cases where interactions means liquid liquid and liquid solid, okay, are purely van der Waals type interaction, okay, VWD type. So, the idea is we want to the S, the spreading parameter, which is the difference of the energy between the dry and the wetted state, we want to relate this with the electrical polarizability of the material, which is the alpha S and alpha L, the solid and the liquid polarizability. Okay. So, we can do this in the following way. Let us think about, we have two surfaces these are two solid surface. So, they will have a solid surface tensions as gamma S V, gamma S V. Think of it, say these are in vacuum. So, there is no material medium. So, these are two surfaces, they are brought together. Okay. So, if this is one surface, this is another surface, they are brought together. So, these are infinitely large solid surfaces. So, what will be the initial, what will be the energy in the first case? So, initially what is the energy? When the two plates are separated, so there will be 2 gamma S V, right. So, it will have 2 gamma S V. Okay. So, upon merging, so they will have, when they are close together, as I mentioned, they have only have van der Waals type of interaction. So, let us consider that on merging, say they gain energy which is purely van der Waals, which is VSS. Okay. And that can be related to the some constant times alpha S square. Okay. So, K is some constant, and that is related to the polarizability, which is alpha S square. Okay. What is the energy when they are in the final, when they join together? What is the energy of that system? What will be the energy in this case? What is the surface energy of the resultant solid? The resultant energy is 0 here, right, when you have the both together. So, the resultant energy is 0, surface energy is 0. That means 2 gamma S V minus the van der Waals VSS, that is equal to 0. Okay. We can do a similar thing where we have a solid or in this case a liquid, say liquid gamma L V, and then we bring the liquid in presence of a solid. So, it has a gamma S V and we merge them. So, you will have a liquid is denoted by this kind of line. So, you have a liquid, you have a solid here, and we can do the same thing. So, this is what is the resultant energy, surface energy when I bring them together? It will be the gamma Ls or SL. Okay. So, that is the gamma, the resultant energy. So, I can write this again as gamma SL, the resultant energy, is equal to gamma SV plus gamma LV, that is the initial energy. So, gamma LV and gamma SV, the initial energy, they interacted by purely by the van der Waals force, which is the V, in this case the interaction is VSL, the van der Waals interaction, and this van der Waals interaction is proportional to some constant alpha s alpha L, because they are solid and liquid. So, they are 2. So, then it is proportional to the polarizability of each of the solid and the liquid. Okay. So, I can have another equation of this. The third case I can have where I have a liquid which is the gamma LV, and also another liquid which is gamma LV. I bring them together to merge to form a liquid-liquid system. And what is the resultant energy of that system? Should be again the 0, resultant surface energy. So, in this case again I can say that the 2 gamma, so this I have created 2 gamma LV, 2 gamma LV, these are initial energies, minus the van der Waal liquid-liquid, which is in this case it will be K times alpha liquid square. Alpha liquid is the polarizability. So, that is equal to 0. Okay. So, I can have these 3 thought experiments and 3 different conditions for this process, right. So, if these are the my key quantities, so this is one quantity, so this is one equation or one constraint rather, this is the second one, and this is the third one. So, if I put all these two together, all these things, so what I will get in terms of the spreading parameter, how I can define down the spreading parameter. So, what is the expression finally coming out for the spreading parameter? Spreading parameter you already know, right, how it is defined. So, that is this expression for the spreading parameter. K, there will be K, correct. So, it will be K times alpha s minus alpha L time alpha L, correct. Because essentially you will have a VSL minus VLL will come up, right, others cancels out, is that correct? So, the van der Waal interaction between the solid liquid and liquid liquid will eventually remain. So, if alpha s, so if alpha s is greater than alpha L, okay, then what we can say is that S is greater than 0. Okay, means it is wetting, total wetting, right. So, you can see the polarizability of the solid and the liquid, the electrical polarizability of these molecules will essentially dictate whether I can get a wetting or not. So, essentially the solid polarizability. So, we can say that the liquid will spread if its polarizability is less than its surface. So, if the liquid will spread on a surface, if its polarizability, if the liquid its own polarizability is less than what the surface polarizability is. So, that is what the chemist does, is tweak this polarizability, so that whether it is greater than 0 to make it completely wetting, or if it is creates a low energy surface to create the opposite. Okay. Is that clear? How the fundamentally we are looking at the fundamental property of the matter and then changing this. These are some of these things are also given here, but one other thing in terms of capillary flow. So, surface tension or the manifests in terms of its capillary flow, because that is how. So, if you look at if I take a a bath of say a fluid and I dip different capillaries. So, maybe this is D1, this is D2, then this is D3, where D1 is greater than D2 is greater than D3. So, a thick very large capillary all the way to a very thin capillary. So, there may be this one may be in millimeter, this one may be in micron, and this one may be in nanometer, right. I can have various capillaries. So, how you see the say any fluid in this case, how which one will lie, right. Say this rise will be say H1, H2, H3, because it will only rise due to the capillary forces, right. So, the capillary will, that is how we understand, right, capillary will try to raise the liquid. So, how H1, H2, H3 will be same or different? So, H3 will be greater than H2 will be greater than. So, thinnest one will have the highest rise of the capillary. Okay. Why it is happening? Right. So, you will have the this creates a much larger height. So, for example, it goes on and on, right. So, can it go infinity, or how, if you have to. So, why it will not go to infinity? So, you are saying there is something so there is a maximum height, right. So, there is H max, correct. So, what balances this basically? So, gravity, right. So, what are the fundamental forces? So, one is surface tension, right. There is the gravity which is pulling it downward, and then there is the viscous forces, right. So, the viscous, the surface tension, and the gravity. So, the balance of this will help to create a maximum rise in the capillary. So, this maximum rise is often referred to as the Julian height of the capillary. So, one can calculate what will be the maximum height in which a liquid will flow. Okay. So, if I know, say for example, if I take in a a capillary of size maybe 100 micron, I know a Julian height, maybe say 5 millimeter or something. I can calculate and find it out, right? So if I cut this capillary, so now I remove this capillary and make it to half, say H max by 2. I've cut this capillary. Half of it, say for example. What will happen? What do you think it will happen? Huh?
So the radius of curvature will
contact angle changes.
So it will try to rise, right? So essentially, if I think of it, this is the reservoir. It will try to rise, and then it will create a bulge, right? Okay, and then it will try to outside. It will have wetting. Okay, so it will wet the outside. So this process was Leonardo da Vinci looked at it, and that's how the fountains in the mountains and so forth he found out. Okay, it's amazing. He was able to relate what is happening in physically, the processes in mountains and so forth, in terms of our current understanding of capillary forces in capillaries. This is just phenomenal. Okay. Now, if I have a capillary which is kept in a, say in a microfluidic system, what you have is capillaries which are in the horizontal direction. So this is the chip, right? Say this is a lab on a chip, and then these are the reservoirs. We have a reservoir, and then this is the capillary. So this is a capillary which is in the horizontal direction, or in the is no longer vertical, is on the plane, right? If I keep a capillary, a chip on this. So now is where is fundamentally this problem is different now. So gravity is not playing a role, right? So then what are the forces in here? So there is the viscous and the pressure, and viscous and the capillary forces. So that's the balancing forces, right? So when gravity plays, so gravity tries to pull this down. Okay, so when it is raising, so there will be, you will see, if you minutely look at these things, even when I cut it to half, there will be some sort of an oscillation of this thing. So that oscillation in the capillary flow is because of the gravity. Okay, whereas in a horizontal capillary, you will never see any oscillation. Okay? So that's very critical. So in a vertical capillary, always you will see it will try to oscillate, and if you have a long capillary, it will then equilibrate into the Julian height. Whereas in horizontal capillary, because gravity doesn't play a role, so there is no oscillation on this. Okay? So that's a fundamental difference between if I have a vertical capillary versus a horizontal capillary. Okay. What will happen if I have to do this thing? Now the question is, if I do this experiment in a spaceship, for example, there is a mission going on, and you put these capillaries, then what happens in there? These vertical capillaries.
So now the contact angle will also change because there is no way.
So the gravity is not playing any role, right? So then it will not have a Julian height, or what? H max will increase. A good point. Think about it. If you have to do this same experiment in a microgravity environment, so what will happen to the your this kind of system, the capillary, vertical capillary.
You will have to notice that it will keep on increasing and increasing.
It will keep on increasing. He's saying you said decrease, right? Increase. And you're saying there will be no Julian height.
But there will not be
Anything to pull. So you try to figure out what's happening. Okay. So the question is, you try to figure out what happens, these phenomena in microgravity environment. Okay. Well, I'll stop here, and in the afternoon what we'll do is we'll meet say around 3 o'clock is good? Huh? 4. Why is what is the particular about 4 than 3? Huh? Is a siesta time for you guys or what? We can meet at 4. I have no problem. But 4 is maybe the temperature outside may be cooler as well. So we'll come back at 4 then, okay, and we'll talk a bit of some other things as well. Okay? And at that time, what I'll do, or what I'll suggest is, you please carry your laptop. We will do some breakout sessions, and I will give you a problem for you to think about based on some of the things that I will talk about in the afternoon, and then try to work yourself through. Okay. So we'll meet at 4 o'clock then.